Okay, so we discussed FRW and de Sitter spacetimes. I mean, de Sitter being a particular case of FRW, and I think most importantly we discussed the Penrose diagrams. So for de Sitter, that was the DS Penrose diagram. It is simply a square, okay, while for generic FRW, so it was some it was a piece. It is a piece of say this of Minkowski or DS Penrose diagram. Whether it looks more like Minkowski or de Sitter, it depends which whether we consider closed FRW or open FRW, right? So for Minkowski, for full Minkowski, it was like part of a diamond like this. And remember that each point of this diagram is a two-sphere, okay? If we're in 4 dimensions, so there's some two-dimensional diagrams that most importantly preserve, most important features, they preserve the causal structure, right? That light travels, so say in this Minkowski space, light still travels at 45 degrees, right? So for generic FRW, as I was also replying to a question, which piece is determined whether the integral, say for some variable eta, which is dt over a of t, is, so let's say we integrate from some t1 to t2, and then if integral is convergent or divergent, at t1 going to minus infinity, and at t2 going to plus infinity, right? So basically the idea is that this range of change of eta, it determines for us whether we have some asymptotic infinity of our space-time. Well, it determines the structure of asymptotic infinity in time of our space-time, right? So for example, Minkowski space, it has this null infinity, and because it has a null infinity, no points, there is no horizon, right? So points never get outside of each other causal contact, right? So any point, signal from any point, it reaches, say, observer that leaves what we randomly chose to be the center of Minkowski space, right? So that is not the case for de Sitter. If we have some observer who leaves, for example, at this pod of de Sitter space, then at some point, say another object that leaves on this trajectory, they are no longer able to send signals to each other. So somewhere around here, all right, the signals emitted that are still emitted at 45 degrees, they no longer, even at whatever, they cannot do anything to communicate anymore, right? So there are different periods. So the first is a period of, like, say, from here, this guy being at rest, the signal stops reaching it, and then so that happens at some time eta naught, and then there is some time eta 1 where they like cannot communicate whatever they do, right? Okay, so that is all very easy to check from this diagram. So and that this signals the development of cosmological horizon. Right, this is similar to a black hole, so we can remind ourselves the Schwarzschild-Penrose diagram. Again, I didn't derive any of this, but these Penrose diagrams are explained pretty well in the book by Hawking and Ellis, if you want to sort of look it up with more details and with careful derivations. But now I'm just sort of telling you that for Schwarzschild, it looks like this. Okay, so this is the Schwarzschild horizon. This is the singularity, and again we see the same properties. Things are behind the horizon, cannot communicate information to stuff that's outside of the horizon. But you can always jump into a black hole and like hit the singularity, right? So the Penrose diagrams are very useful for analyzing the structure of spacetime. Okay, so then let's and then I said for FRWs, it depends how the scale factor changes. Let me also review for you these different patches of the Sitter space. So there was there is a Poincaré patch that corresponds to flat slicing. And let me draw. I forgot which color I used last time, but let me write it in blue. So these lines are all asymptote to this horizon. So the metric, so the Poincaré metric.
This part was messy.
Sorry?
This part was a messy, right? Blue part.
There are no blue lines are the lines of let me call it T Poincaré equal const. And now let me write down what is the metric in this blue slicing. The metric is minus dt Poincaré squared plus e to the ht dx squared. Okay. Now the white slicing, that will be just the global time. Okay. It just goes horizontally. Let me not continue not to make the picture too messy. So this is Poincaré. You see this each and these blue lines are lines of constant Tp. Okay. So they are just flat three-dimensional infinite universes. Okay. So now I have the global slicing. And here, okay, maybe I can put, to keep the units right, I'll put h squared here. And here I have d s of s3 squared, which is the sphere of unit radius. Okay, so that is dimensionless, the metric. So you see each line, each white line is a three-sphere, okay? And each blue line is an infinite plane. So the spacetime is you can think of the Sitter as a closed spacetime. Closed meaning it's a compact spatial slicing, but it's expanding so fast that you can also slice it with three-dimensional, but infinite in size planes, right? So it's the same manifold. And finally, we also discussed the static patch. So static patch constant time slices look like this. Okay. Let me look it up so that I don't mess up writing down the static patch metric. So the ds static is minus dt static squared times 1 minus r squared plus dr squared over 1 minus r squared plus r squared d s2, okay? And I should make, okay, to h squared here, h squared here. Okay? Good. So now what is this static patch? So static patch is the maximum region of the zeta space where we can choose a metric so it does not depend on time, right? So it, in other words, it has time like Killing vector. And the causal, sort of the implications from the point of view of causal structure is that so static patch is not unique for the zeta space. In fact, we can pick any time like geodesic, call it an observer. They all can be moved into one another by the isometries of the zeta space. Then with respect to this observer, so here I chose this geodesic just going vertically on my Penrose diagram, at the edge of my Penrose diagram. So remember, every point here is S2, but a point over here is just a point that can also be seen from this way of parameterizing the metric, right? Because with r equals 0, so this is r equals 0, this line in the static patch coordinates. So the sphere shrinks to a point, right? So this is like this red region, okay, inside of this red triangle. So this is a region of a proper size, which is the size is of order h minus 1, okay? So that's the inverse Hubble radius. That is a size. On this Penrose diagram, it doesn't look like it's sort of constant, like it's static, right? It looks like it's changing. But actually, the metric on each of these red lines is the same, right? I mean, it's manifest from the equation. Not very manifest from this drawing, but from this equation, it's manifest, right? So the universe is just of the size. Because r changes from 0 to h minus 1. As you see, this metric becomes singular, right, when r approaches h minus 1. So it's the portion of the universe of the size of the inverse Hubble scale, okay, inverse curvature scale, that is accessible to a single observer. Accessible in the sense that he can receive information from any point in the space-time, and he can send information to any point in the space-time. Of course, if this point is not in his past light cone, okay? But as long, throughout his entire history, he can communicate with any point inside of the static patch, right? Very good. So, and then we wrote, so these metrics look quite different. As I said, it's not, one can check that all the curvature invariants agree and find explicit maps between those metrics. And the easiest to do it is through the embedding. So we can embed the zeta space into the Minkowski, 5-dimensional Minkowski space. This thing equal to 1, I guess. So this guy is a hyperboloid. So this is my R1, 4, 5D Minkowski space, and this embedding is this connected time-like hyperboloid. Okay. That is expanding exponentially. It's most manifest in this global slicing that cover the entire hyperboloid. Right? Any questions? So that is roughly what I explained where I finished last time. Are there any questions about it? And I wrote explicitly these embeddings, and I said the best way to sort of check how all these coordinate systems are related to each other is through connecting them through these embeddings. Okay, let me not copy them because it's massive formulas. Good. So let me talk a little bit about, so what I want to do in this lecture, I want to now talk a little bit about possible observables in the de Sitter space. And then we will sort of remember our picture, the history of the scale factor that we assume is true for our universe. And then we will see what are then the meaningful observables for our actual universe, which has some regions that are like the de Sitter space, but that is never exactly the de Sitter space. Okay, and then after that, I will talk about, I will briefly talk about quantum fields in flat space, that again I mentioned a little bit in the previous lectures, free quantum fields in flat space, and then we will discuss a little bit the free quantum fields in the de Sitter space, and try to illustrate how this idea of the origin of cosmological perturbations, how it appears from this picture. Okay, good. So let me talk about observers. So first, I also wanted to mention briefly the symmetry group of, or group of isometries of the de Sitter space. So if we consider rigid de Sitter space, and this is what that's what I'm talking about, right? I'm not talking about perturbation. I'm basically not talking about general relativity on these backgrounds. I'm really talking about this fixed metric, right? So if the metric is fixed to what it is, then the isometries are well defined, and they are isometries of this 5-dimensional Minkowski space, right? Because, well, not translations, but the Lorentz transformations, when acted on this 5-dimensional Minkowski space, they leave this equation invariant, right? Because this is just the norm of a vector in 5-dimensional Minkowski space, right? So Lorentz transformations leave it invariant. So now in 4 dimensions, the Lorentz group is SO1, 3. So in 5 dimensions, the Lorentz group is SO1, 4, right? So this is the group of isometries of the de Sitter space. So now these various patches, they partially break these isometries. For example, the static patch no longer has this entire symmetry group, because some of these generators, they will move around the static patch. Okay. Of course, the global de Sitter space, it has all those isometries because it covers the entire de Sitter space, so it does not get shifted. A little bit less obvious is that Poincaré patch, namely this upper triangle, is also around under all, at least all transformations of that group that are connected to the identity. Okay, so now, one thing I wanted to mention. Okay, so there is also a nice, again, if you want to get some more intuition about this thing, there is a nice exercise is to check which isometry is static patch is TS translation. So you see, this is a little bit not obvious, right? Because all these generators, they have some sort of boosts or rotations, right? We don't have any like translations right, inside the Lorentz group, but somehow, but there is one of the boosts, basically, one of the non-compact generators. Once it acts, once we parameterize the de Sitter space in this static patch coordinates, it simply shifts the static patch time by a constant, right? It becomes translations of the static patch time. So I think that's, if you remember, if you take the equations for the embeddings that I wrote last time, then I think it's a nice exercise to see how some of the generators of this group become these translations of TS. And that, well, that basically will also show that we cannot, that this generator only looks like time translation in some region, but not globally, because globally it's more like a boost. So it's more like some hyperbolic transformation as opposed to some killing vector that is globally time-like. Okay, so now let me come to this important question of observables. So the idea that in Minkowski space, and we see observables, when we just have quantum field theory, that's an important conceptual point to keep in mind. When we just have quantum mechanics or quantum field theories, we can be a little bit more flexible with what observables are. For example, correlation functions of some local operators are observables. Now, once we have general relativity, and then more, even more importantly, when we have quantum gravity, then defining observables becomes more subtle. The reason is that observables should be diffeomorphism invariant, right? Because once we have a general relativity, things that make sense are diffeomorphism invariant. That stays true once we have quantum gravity and quantum field theory. So now, having just local operators inserting at some points in our de Sitter space, and measuring, expectation values of these operators. So expectation values in quantum mechanics use expectation values of operators. In quantum field theory, we usually use the term correlation function of operators, but really, and I'm used to using it, but really it's just expectation value. So we have some operators in our theory, okay? Say we have some operator O, and then if it sits at some point x1, and then maybe another operator that sits at some point x2, right? So we can imagine computing the okay, well, let me erase this matrix. We stared at them last time. So I want to discuss this question of observables. So naively, we could consider expectation values of operators. Say this O of x1, of x2, and this can be any operator, any favorite operator, a momentum of some particle or whatever in your that lives in your de Sitter space. But the problem is that this is not diffeomorphism invariant, right? Because it's not from GR. I mean, okay, we pick some coordinates. Okay, I just erased 3 different coordinate systems, right? But once we have fluctuating metric and general relativity on the space-time, then I can do arbitrary many redefinitions of my coordinates. They're all equivalent, right? So what is x1, x2? So this is not gauge invariant.
So why I don't know, because it seems like this stuff is scalar, yes, and scalar should be invariant.
Yeah, but not, so it's a scalar function, right? So it transforms when I do some diffeomorphism, x goes to f of x, right? So this guy goes is O of, so say this is some function of x1 and x2, right? So we pick some coordinate system, we computed it in some ways as a function of x1 and x2. Now we do diffeomorphism, x to f of x, right? X mu to, you understand, right? Okay, I'm not used to something like this, right? Some generic diffeomorphism. So then this becomes, so say this some function, call it g. So then this g goes into some different function, right? It now becomes some function of f of x1, f of x2, right? So it will change. And there is no preferred way parameterizing our manifold once we are in general relativity. So that is the problem. Okay, so now you will say, well, that shouldn't be like a big problem because in real world we have general relativity, and of course we kind of still measure in distances and like everything, right? And the way we do it is that we always have what we really do, we have some anchor point, which is, I don't know, say our laboratory or whatever, like Earth, okay? And then we measure everything. We use geodesics. We basically always, even though we don't do it in practice, but when you do some cosmological measurements, that's really what you do. But if you want to be precise, that's what you always have to do. You always have to stretch some geodesics from some anchor point, okay? And that object will be different variant. So basically what we do in real life, we have some laboratory that has that is some world line, okay? And then these are our operators, say this x1 and x2. And what we do, we basically send like a bunch of geodesics from our laboratory lines. So these lines, I'm drawing them wiggly because genetically metric is curved, right? Because there is some gravitational field of Earth, gravitational field of those objects can be small, but like if we want to be careful, we have to define it, right? And then, so these are geodesics. And now, once we fix, if you draw enough geodesics, that like uniquely determines the point x1, right? Because if I know this, if I triangulate everything, right, for a given metric, for a given curved metric, that determines unique to this point x1 in terms of lengths of various geodesic segments, right? So this is a way to define observables in a different variant way, and that also works in quantum mechanics and in quantum field theory once the metric becomes a quantum object. Okay, so there is no big surprise about it. It can be done. So now, and you do the same for the point x2, but it's a much more complicated thing than just having a function of 2 points. Now we have a function of a bunch of geodesic lengths. Okay. Good. So now. Why that becomes complicated? So that's what you could do in general. Now, what we can do instead in flat space, so this is a generic procedure. Now, in flat space, we can often assume that metric at infinity is fixed. So there are no diffs. So this is my flat space, and I can have metric fluctuating. Sorry? No diffeomorphism. Diffs is diffeomorphism. Yeah. No diffeomorphism. Diffs is just diffeomorphism. It's a long word. I raised it right. No diffs on the boundary. So it's consistent to consider Minkowski space where we have diffeomorphism invariants. And we're only allowed diffeomorphisms that vanish at the boundary fast enough, okay? Because we can keep the metric asymptotically Minkowski. So that actually defines Minkowski spacetime in general relativity and in whatever quantum gravity or something. We can say that Minkowski spacetime is just an asymptotically Minkowski spacetime. And in particular, the group, the Poincaré group. You're familiar with this notation, so SO13, this is a Lorentz group, and I, whatever stands for translations. Basically, this is a Poincaré group, is a global symmetry. that is because even though locally there are diffeomorphisms, so it's unclear, you know, what, I mean, we can have some black hole in the middle of our Minkowski space, so metric is like Schwarzschild, so it's not clear what, like, you know, Lorentz black hole is not invariant under the entire Lorentz group, right? And whatever, any generic metric perturbation. But if we only consider metric perturbations that vanish close enough to my boundary, and boundary, remember, is this two null surfaces, right, that I call past infinity and future infinity Minkowski space. So diffeomorphisms vanish, and then we can still have the Poincaré group that basically acts on these boundaries, okay, and that remains a global symmetry of a space. And so it stays well defined what is the global symmetry of Minkowski space when we have diffeomorphisms. And that is, I mean, this is related to the fact, I mean, it's not a coincidence that I'm talking sort of simultaneously about the symmetry groups and observables, because these are sort of closely related notions. The reason that we have asymptotic, whatever, the reason, logically these are connected, even maybe I'm not explaining all the logical steps why they are connected. But the idea is that we have the symmetry group acting asymptotically, and it makes sense to have the metric perturbations vanishing asymptotically, allows us also to define asymptotic observables. And the asymptotic observable, sort of the most well-known asymptotic observable in flat space, is the S matrix. Okay, so S matrix is stuff when we send something from past infinity, okay, and then we catch it, or particularly from this point. Say massive particles, they may all originate from this point, but okay, doesn't matter. And then we catch stuff at the future infinity. And because we don't have any diffeomorphisms acting here or here, okay, then we can define, and because we have the Poincaré group, we can define this asymptotic states in the same way as we would do in just flat Minkowski space without having any diffeomorphism invariance. So at least conceptually, it's not social. It's known how to define observables even in quantum gravity in asymptotically Minkowski spaces. Okay, and in particular the scattering matrix. So this defines. Okay, let me erase this stuff. I'll come back to it in a moment. So the S matrix is well defined in quantum gravity in asymptotically Minkowski. Okay, so this is a generic procedure, so that kind of works in any spacetime. While in flat spacetime we can have like a more a much nicer observable, which is really, I mean, the scattering matrix from which I used to since whatever quantum mechanics or classical scattering theory or whatever we first encountered the scattering matrix, right? Good. So why am I telling you all this? Like, it may not be obvious to you at this point why this is much nicer than this, but I hope I gave you a flavor that I mean, this is really the usual thing we encounter in quantum mechanics. This looks like a mess, because I mean, even like a simple expectation value, you need to draw a whole bunch of geodesics to define it, and becomes something complicated. And if you actually try to compute something like this in practice, where gravitational effects are important, it becomes a total mess. And it's unclear how, and most importantly, it's unclear how to make this thing well defined non-perturbatively. Why? Because there is too much back reaction, right? So of course, when we're around some nice space-time, we kind of know what geodesics are. But if somehow one of these objects actually collapse into a black hole, right? So then there's some mess happens with these geodesics, and like, what are we going to do with them? While here, it's all fine. We can have as many black holes getting created here in the middle, and some weird stuff going with space-time. But asymptotics we keep fixed, and then the SS matrix is believed at least to be well-defined non-perturbatively, say be unitary non-perturbatively.
So what in general we want to get? Some just observable.
Yeah, we want to get some observable. Yeah, our goal is relatively modest here, if you might, but that's what I'm going to tell you is that at the moment for the Sitter space, we do not. I mean, no one knows how to define any observable that we will be sure that is well defined non-perturbatively. So this is really a hard task, as it turns out.
Okay, I see. For example, we can observe scalar perturbation spectrum, and as I understand, we just calculate this stuff that you.
Well, yes, we'll get there. But you see, so far I'm not, and it will be important. So that the scalar perturbation spectrum, this thing that I mentioned, that we don't live in a pure de Sitter space. Okay, but for now, our discussion is we're trying to be in the pure in the Sitter space. Okay, not in some installation with that. Okay.
So and in the Sitter space, it is easier to calculate this stuff.
No, in the Sitter space, I'm saying it's not. I mean, you can calculate several things, but what's complicated in the Sitter, no one knows how to do, is how to define a single observable that actually. And I mean, of course, when, as I said, all of this when gravity is turned on, and when we want to we want to define observable, at least in principle, with arbitrary precision. And I'm saying I was about to tell you that in the Sitter space, no one knows how to do it. Okay, so the fact that in flat space we have at least one observable, which is the S matrix, which actually is a very powerful observable, because I think it is very good. It's very valuable. Okay, it makes flat space conceptually say much easier to study than the Sitter space.
Okay, so am I right that all that we want to get is impossible to get as S matrix in the Sitter space?
Well, yeah, that's what I was, because you see, okay, now let's come back to, I first try to explain to you that it's possible to get it in flat space. Okay, let's say we believe in this, okay, for a moment. I was saying that in principle, careful definition of S matrix in flat space requires, some bells and whistles with, keeping track of which diffeomorphisms we allow, which we don't allow. But okay, let's say you believe me that it's all doable, and S matrix can be well defined in flat space. So now we transition to the Sitter space, okay? And here we sort of stuck. We're stuck even at the question of defining the symmetries. So I said that in metric fixed. G mu nu, or if there is no general relativity, no dynamical metric, so then isometries of the Sitter space is SO1, 4. By the way, it's the group that has the same dimensionality, right? I mean, so this group is 10-dimensional, okay? So there's 6 Lorentz, 3 rotations, 3 boosts, right, and 4 translations, okay? So this is 10-dimensional, and this is also 10-dimensional, right? Because this is, it's the same as SO5 dimensionality, right? Good. So now, what is, so when gravity becomes dynamical, it's not very clear how to define the isometry group of asymptotically de Sitter space. So question here, there is what is asymptotically de Sitter? And the point is that we don't know. You could say, well, why don't we do the same thing? Why don't we freeze metric fluctuations, say on this boundary and on this boundary, right? But this is not what one is allowed to do, because here this boundary is really in the future, and you cannot, it's not okay to say that we're fixing the metric fluctuations in the future, because okay, it's acausal, right? You do some stuff and it produces a metric fluctuation. You cannot demand that they vanish at infinity. Now you may say, well, why don't there is maybe a similar problem in Minkowski space. And I kind of put it under the rug by telling you that S matrix is fine. In fact, I cheated because S matrix, if you remember quantum mechanics, is not really an observable. It's a cross section that is an observable, right? It's like some sort of square. S matrix is like probability amplitude. And amplitudes are not observable. What's observable is an actual probability, but that's okay. And the reason is that in Minkowski space, we don't have to fix the metric fluctuations at the boundary. What we can do, we can say that the total amount of energy that we have in our scattering experiment is fixed, and energy is globally conserved in Minkowski space. Now, if energy is conserved, then all metric fluctuations will decay as like 1 over r or 1 over r squared, depending if we look at the potential or whatever. So they decay fast enough at infinity. If the energy is finite, they basically by themselves go to zero fast enough. And that's related to existence of this asymptotically Minkowski space in general. So it's all fine in flat space. De Sitter space, if you think of it in global slicing, there is no infinity, right? Spatially. So these fluctuations do not decay fast enough. Of course, the universe grows, so you exponentially, so you may imagine maybe that's enough to kind of dilute and dissipate the fluctuations, but that has not been made precise. So we do not really know how to carefully in quantum gravity, even in perturbative quantum gravity, how to estimate. I'm not saying that it's undoable task, but it hasn't been done yet.
So could you repeat? What's the problem to set this perturbation to 0 on plus infinity?
In De Sitter, this thing.
Yeah.
Well, that is because you're trying to fix your future.
Yeah, but it seems okay because we know that our universe is expanding and maybe all of this perturbation are going.
But there is something. Okay, I'm kind of running ahead of myself. But if we get there in this lecture, or if you just say believe me, right, that there is this constant creation of quantum perturbations in De Sitter space, because De Sitter space, importantly, is not static, right? So energy is not conserved. There is no globally conserved energy, right? Because no globally conserved time like Killing vector. So you can think of De Sitter space is constantly driving at the quantum mechanical level production of some fluctuations. So it's true that it grows and things kind of get dissipated, but also they constantly get regenerated. And which dominates is not obvious. Okay? Yeah, it's basically like creation. It's true that they always start flying away. So kind of, if you just put some gas in the De Sitter space as in any expanding for W, it will cool down and kind of go to the ground state. But at the same time, this expansion always drives constant particle production. Sort of similar to Hawking radiation from whatever, if you know what it is. So basically, that is the problem, and we do not know how to do a reliable calculation to say that one dominates over the other, say that the dilution dominates over the other. Good. So that makes a problem, and at least it's too naive. It's believed to be too naive to simply fix the metric here. Okay. Or to say that fluctuations should decay with some law or whatever. So that is not even understood. So now even if we fixed something, somehow we solved that problem, okay? Then there is a next level problem that if we want to do some experiment, okay, let me erase this, too many lines. If we want to draw, if we have some experiment happen and some stuff went here, some stuff went here. Now this is very bad as far as observable is concerned, because here in Minkowski you can imagine, and that's actually close to what's going on, there is a particle detector that moves sort of on this line over here and just collects all this information, right? And indeed measures it. Now here we cannot have a particle detector moving like this because it's a space-like, nothing can move in the space-like direction. So there is no single observer that measures even a fraction. Remember, once we get closer to this line, the particle horizon on this picture, I'm drawing here the horizons of various observers, becomes smaller and smaller. Okay, it's constant in proper size. It's a Hubble radius. But because the universe is growing on this picture, it becomes smaller and smaller, right? So now, I mean, no one can measure, more than kind of one particle that that goes out in that direction. Okay. And I mean, we will explain how to sort of get around it in some other models, but in pure de Sitter space, that does not look like a nice observer. Like something setting up something like this, it's not obvious that it's a nice observable. Okay, that's a big question. But then there is a view on de Sitter space that basically we say that it's only some observables restricted to a static patch that are well defined. Okay, so this thing was a static patch. But that is something very different conceptually from, say, the S-matrix thing, because we only keep one point at our future infinity, right? So that seems like that's actually a very small fraction of the Sitter space. And saying, yeah.
But this point is S, or is a sphere, S3 sphere.
This point is not really. It's a sphere of the size of a Hubble radius. Yeah, so it's not a point. Yeah, it's a sphere of or a ball, whatever, of the size of a Hubble radius. But it's a measure zero set on the future infinity, right? Okay. So now, but maybe that's all there is. So maybe only. Static patch. Observables make sense. So now, the reason I did not erase this picture, that to define something inside of a static patch, you really need to go to all these complications with geodesics and whatever, because then you imagine this as like your laboratory, and then you want to measure some expectation value of operators here, for example, but you're not sending them to infinity, so metric fluctuations never die, and then, okay, you need like all your geodesics to connect them. So it comes back to this complicated picture. It's not clear. Can we make sense of it, non-perturbatory or whatever? And then people try to do some other things, define observables on these horizons, whatever. But I just wanted to emphasize to you that this is not like this is still an open question. Good. Let me then, okay, here I talked about this abstract de Sitter space, and then it's not obvious that this, so this makes some people think that maybe we should not consider this pure de Sitter space as some physical object whatsoever, that we should, always think that it's approximation to something, okay? And then in the beginning of last lecture, I told you that it's actually a good approximation to some periods of evolution of the universe. And now let's recover that picture and see, how our observables that some of you mentioned and I also mentioned, namely these primordial fluctuations, even though I claim that they actually can be sort of calculated in the Sitter space, how they are observable. Okay, let's discuss this. So for this, we recover our picture of the scale factor as a function of time, okay? And again, let me assume that inflation was actually true, so I draw it as so I have some e to the ht here, and then I have some power law, and actually this alpha is smaller than 1. For example, you remember we had like now we know the alpha is smaller than 1, we had this formula like t to the, depending on the equation of state, and then if we put a state that has no pressure, we get something like t to the 2/3, I think, or whatever, so it's smaller than 1. And then here we get another period of exponential expansion, with e, say e to the h naught t, and that is what we basically after discovery of a positive cosmological constant, right? You probably have heard about discovery of cosmological constant in 1998. So since then we know that the universe is expanding, you know, dominantly like an exponent again, right? So now let's draw qualitatively the Penrose diagram of our actual universe, okay? At least the regions that we know. So remember that brings us back to computing this integral. Sorry. And see how it behaves. So over here we have some portion of the Sitter space. Okay, and let me do, just for simplification, let me imagine it, we actually live in a closed universe, okay? Just drawing will be a little bit easier. It may well be true, we're just seeing a small portion of it, okay? So, because I said we're consistent with the universe being flat, but okay, maybe it's like a small part of the sphere that we see, that's why we don't see the curvature, right? So let's just do this for, it's a little bit simpler. Because then I can say, okay, this is dt over at, but it's an expanding part of the Sitter space. So this e to at is the same as cosh ht when we're in the upper part of this diagram, right? So I draw for this period, let's say, I'll draw color coding, okay? So this is like a red period. Okay, color coding is not the same as I had for static patch or whatever. I'm new color coding, but I hope it's clear. So this, I say, it's a piece of this. It's a piece, some sort of middle piece of this. Maybe middle piece like this. Okay, of this de Sitter square, right? It's not. Let me here draw like a wiggly line. Because it's not a boundary, it's like this, okay? I cut out a piece because it's a finite extent of extent in time, okay? Now I have this, let's say, blue period where I have power law, okay? I could be something in between that we do not know, but let me ignore it, okay? So now what happens here, in the blue region, because t is smaller than 1, the integral diverges at future infinity, right? So now I get like, if this blue period lasted forever, I would actually have like an open Penrose diagram, okay? Because the integral in eta diverges. Eta diverges because the integral in dt diverges, right? As we say. However, then what happens, we come back to this, okay, this will be just a white region, which transitions us to exponent that actually converges. And let's imagine for a second that this just goes on forever, okay? All right, that again. No, then we have again our hat like this, right? So we got a tall, Penrose, sort of elongated Penrose diagram of the Sitter space, okay? And we leave currently, let's say we leave, you know, somewhere here, okay? We just transition from blue to white, right? So what happens now? Well, okay, sorry, I drew this. It's too long, the blue region that I took. Okay, let me not exaggerate this too much. Okay. Good, because I don't want, I mean, you'll understand why. So now, let's see what we, so if, okay, let me now draw. If we never transition to blue region, okay, then the Penrose diagram would be like this. Okay, and then there is a cosmological horizon. So none of these points are outside of causal contact. But because we transition to the blue region, all these points, they again got into causal contact, right? They can communicate again, okay? And then if there was no white region, then the blue would go on forever, and eventually the entire universe would be seen to the observer if he lives long enough, okay? But currently, with the diagram that is in solid lines, right, we're in kind of intermediate situation. So if we look back, by looking back, meaning that we collect our past light cone, we see some large fraction of this original de Sitter piece, okay, which we think is the conjecture, but okay, now for now we say take the inflation as a real thing, okay. So this is what allows us. So this is what's called, from the point of view of this red de Sitter space, where people call it meta observer. So we basically fulfilled the goal by transitioning to a different space-time, okay? We managed to collect some part of information from the space-like region that would be impossible for an observer that lives just inside that de Sitter space, okay? So that allows us, in some, at least in some models, to get away from this problem of all these points being causally disconnected and separated by the horizon. Okay, very good. So now I'm going to argue the following. So first I'll draw the cartoon, and then I'll try to do some equations for the. Okay, I have about let's say 50 something minutes. First I'll draw the picture for you for what happens. So I'm going to argue that the quantum fluctuations on this wiggly line. Okay, so this wiggly line I'll refer to as the reheating surface. So fluctuations, so fluctuation of quantum fields on this wiggly line, they can be calculated as long as this region is large enough. They can be calculated without the prior knowledge, without knowledge of initial conditions over here. Okay, so this is irrelevant for computing quantum fluctuations, at least on this part. So say this is, let me call it the reheating surface, like observable part of this wiggly line is the reheating surface, okay? Really this thing I call reheating surface. Irrelevant for computing fluctuations, quantum fluctuations. Okay, I ran out of space. On reheating surface, which is this region, okay? And then, once we do this calculation, then these fluctuations, they become, they grow and classicalize, as I said, and then start producing, galaxies and black holes, whatever, and eventually generate like our galaxy that flies somewhere here, and some other galaxy that we can observe, and whatever, and all the perturbations. Say, okay, that's what I announced last time, but this is now trying to, put it on some more scientific thing, which is this Penrose diagram. Okay. Very good. Any questions about where I'm going? Let me check my notes if maybe I wanted to say something and forgot.
Why do we live on the edge of...
Oh, this is a choice. As I said, as a here, I mean, this is, I decided, when we map our actual space-time into this Penrose diagram, right, we have some choices to make. I mean, our goal is to map the entire space-time into something compact. Okay, it's convenient to pick our, position. I can set it to, I can move it to the edge. Same as for Minkowski space, right? There is no preferred center of Minkowski space, but if you do some scattering experiment, it's maybe convenient, as you always choose coordinate systems, so you do it at r equals 0, right? And then stuff flies at r equals infinity. So it's the same thing over here. say if we live in a closed universe and each slice is a sphere, and then we can use isometry's rotation of that sphere to always put like, at some point at a sphere that we call r equals 0 in some coordinate system, right?
But we say that the enough observer leaves later than our law ended. So it's not like the transition point.
No, we are a meta observer for this red de Sitter space, right?
Yes.
What's your question?
So it feels to me like meta observer is a transition point between the power law age and the age of exponent.
Here? Yes. No. Here it was a bit of a coincidence. Sorry, I meant that we already leave. Say, yes. Well, we kind of leave close to the transition, but it doesn't matter conceptually, right? Already once you are in the blue region far enough, you already see a large chunk here, and then the point is that because of this future, so if the dashed line, blue line continued forever, there would be an ultimate meta observers who would always see the entire universe, right? Because of this white line, the best meta observer sees just a little bit more than say we do now, right?
Yeah, but the ultimate meta observer will live somewhere in the infinite future.
Well, yeah, I mean it's not like this meta observer thing is not something extremely well defined. Okay, it's more like a term for a guy who sees more than 1 point. So let's put it this way, right? So more than one Hubble sphere of this red spacetime. So as I said, the ultimate meta observer would exist if the spacetime expanded as a power law or whatever forever. Then he would see everything, but here, there is not big difference between us and someone who lives at infinity, if really we're in the exponential expansion, right? As you can see from this diagram. Let's do this a little bit of this quantum fields, but I'll do it. I first wanted to do some more technical calculations, but then I decided to do more of a bit more of a dimensional analysis, because I think it will be a little bit. I mean, if you know quantum field theory, then these detailed things will be boring to you. If you don't know quantum field theory, probably you wouldn't understand much. But let me try. Okay, I erase this thing because we have kind of our new Penrose diagram now, and let me do a bit more of quantum fields. Okay, so we'll start with free quantum fields in Minkowski. Okay, good. So as I told you, we can have some say a Lagrangian, which is an integral dt or whatever the action, say integral dt d3x, and then we have the gradient phi. So we have a kinetic term phi dot of x squared, and then we have the gradient term di phi squared. Okay, and then we can go to momentum space. We get a bunch of harmonic oscillators, so we can go to momentum space. Integral dt d3k, and here we still have phi dot squared that now depends on k and t, and then plus k squared. I guess it's going to be a plus. No, it should still be minus, right? Minus k squared phi k phi minus k Okay, good. So here I just Fourier transform, and so here it's more clear that it's harmonic. It's still a little bit, not really, because I have like phi k, phi minus k, the real harmonic oscillator. So here it's also, actually I should write it like this: phi dot k, phi dot minus k. Okay, so it's a little bit more subtle than just a single harmonic oscillator for each k, because it's actually modes with k and minus k that get paired up, right? That's because of momentum conservation, right? I mean, if the total, this object has, I mean, this d3x integral projects our on, what's wrong? Yeah, well, that is, I mean, I did, okay, I'm skipping steps, so I should be, I just write phi, let's do it, I mean, phi of x is integral e to the I kx phi k, right? Okay, so now we plug it in here. Let's ignore the dots. I mean, we just have integral d3x phi k dk, right? I mean, here we have integral e to the I kx phi k dk, integral e to the I, say p x phi p dp, right? So now let's take integral dx. That will be an integral, that integral dx will give us a delta function, right, of p plus k. So now we have integral dp dk delta of p plus k phi p phi k, right? So now this sets p to minus k, correct? That's right. That's that's just Fourier transformed. The general law is whatever you have, when you do like a convolution of Fourier transforms, what survives is the, I mean, if you start with an integral d3x, what should survive is something that has total delta function of all the k's, right? So for two of them, I can solve the delta function. It's phi k, phi minus k. So it's almost a sum of sum of pairs of harmonic oscillators. One, I mean, that kind of for k and for minus k, okay? But let me ignore, I'll be ignoring, if you do like careful quantization, take care of it, but I'll be ignoring it. I'll just say that this is just a bunch of harmonic oscillators and a bunch of like single harmonic oscillators, and that will get us where we need. So now let's try to estimate. So what if I compute, so phi is now, I mean, it's important, that phi is not a wave function, okay? It's a field which is, it's an operator, okay? So when we quantize, we promote this phi to operator, okay? So phi is, you should think of phi k as x of harmonic oscillator. So let's remind ourselves the standard harmonic oscillator, right? So standard harmonic oscillator, we have a Lagrangian harmonic oscillator. We'll have a Lagrangian which is x dot squared minus omega squared x squared, correct? That's a harmonic oscillator. I mean, I said mass to 1, whatever. But frequency, that's important. Frequency is omega, right? So these are harmonic oscillators with frequency that goes like k, which of course what we expect, because this, we remember, we took it as basically some simplified version of the electromagnetic wave that, as we know, has omega equal k, whatever, right? I'll put equal. Proportionality, meaning that there could be some c or whatever, but really it's omega equal k, right? So that's clear from relation to this harmonic oscillator. So now so what is a 2-point function of phi of x1 and it says a moment of time t and phi of x2 moment of time t. So I quantize this. I said this is an operator phi. Okay. So now what is it? What is the 2-point function? Well, let's remember our dimensional analysis. So dimensions of phi was mass dimension was 1, right? That we did Did we do it last time? I forgot in which. Maybe I did it in the QCD lecture, not last time. Okay, let's do it. Let's do it here. So action is dimensionless, right? So this has coordinate dimension 4, right? So derivative, which means mass dimension minus 4, right? So now derivative has mass dimension 1. So field must have mass dimension 1 for this thing to be dimensionless, right? So as you remember, I mean, again, I remind you, mass has dimension 1 and coordinate has dimension minus 1. I'm not talking, I mean, coordinate, whatever, not referring to here, I'm referring to space-time coordinate, okay? So now, what is the two-point function? Two-point function, what can it depend on? It can depend, it should be Lorentz invariant, right? Okay, this whole thing is Lorentz invariant, of course. Well, I could have written it this way, right? As d mu phi, the integral d4x, d mu phi, right? So it is Lorentz invariant, the whole thing. So the two-point function should be Lorentz invariant. Can only depend on this interval x1 minus x2, right? Because times are equal, so dimensionality should be minus 2. So it must be 1 over x1 minus x2 squared, okay? Not 1, I mean, it should be some number, or a 1 number, because there's nothing else over x1 minus x2 squared, right? So that's what the expectation value of this operator is in flat space. So now let's Fourier transform. Let's Fourier transform. So when we Fourier transform, then phi k, phi minus k will be, what is a Fourier transform? It's a Fourier transform of d3x, right, over x squared. So this has dimension, again, I'm just doing dimensional analysis. So this must be 1 over k, again, with some Orman constant, right? Because this has dimension, mass dimension minus 1 now, right? We can also check from here. It's a little bit subtle. So from here, what is the mass dimension of phi k? So dimension of phi k, right? Because phi k is an integral of dimension of phi k is minus 2, right? Because it's an integral, it's a d3x, integral d3x of phi of x. So this has dimension 1, this has dimension minus 3. You guys will be surprised how much is done with dimensional analysis in fundamental physics. And you check all your calculations. It's super important. So now this has dimension minus 2, right? But then you say, well, why do I have 1 over k? Anyone understands why by dimensional analysis phi k has dimension minus 2? So naively, I would say that phi expectation value should be something like 1 over k to the 4th instead I have 1 over k. Does anyone know where the 3? Well, those who took quantum field theory know, but someone who just looks at this dimensional analysis. Anyone understands why I'm missing? Why dimensions do not match here? Okay, I mean, this formula is a little bit sloppy. Really, I should have written the formula like this. Okay, so now that makes sense. That has dimension minus 3, right? And then the only thing that can have non-zero expectation value is when k and p, when momenta is conserved, okay? The reason is clear, right? Because if I have here a parity invariant, it's the same thing as for harmonic oscillator. Expectation value of x is 0, of course, right? In the ground state. Oh, by the way, I should have said, I'm computing this expectation values in the ground state of this system, okay? In the vacuum, right? So this is 0, while this is 1 over omega, right? So this maps, remember that we had omega equal k, right, here. So this agrees with this. But we need to take into account the fact that, that if we have, it's like if you had several harmonic oscillators, right? For example, we can have like 2 harmonic oscillators, x and y, right? So then we would have like the expectation value of yx should also be 0, and expectation value of y squared should be omega, right? 1 over omega, if they have the same frequency. So this delta function is tells us that off diagonal expectation values should be 0. Okay, that's why we have this delta of p plus k. And this can be derived carefully if you just do, you know, the most boring thing by, you know, canonically quantizing this thing, and you'll need to at some points kind of refer to Lorentz invariant, so quantize it in a Lorentz invariant way, and then you will land on the same answer. But we get it correct from dimensional analysis. Okay, so what does it teach us? What does this formula teach in position space? Let me put 1 here. We do not care about the sort of 1 constant. So this is important that at long distances, quantum fluctuations are small. Okay? So this, we can repeat the same thing for electromagnetic field or for any quantum field, and we'll get, well, roughly the same answer, that these quantum fluctuations are small when we go to large distances. The decay here is like 1 over x squared. Okay, that's why we do not really care about them. So something very interesting will happen in a moment when we put our theory in the Sitter spacetime. Are there any questions about this? Okay, so now finally let's get to see where I want to keep.
I'm sorry. General property of quantum field theory that correlation function decay at large distances, because in quantum mechanics we like have Bell inequalities, and it is not.
Yeah. In quantum field theory they decay. So the reason is that at large Euclidean, whatever, at large spatial separations, the correlation functions always decay in quantum field theory. And I mean, the reason you can sort of still transmit signals is if you go, say, on a light cone, right? So then this gets replaced, of course, with like 1 over the interval. So if if your interval is still close to 0 because you send a signal, on the light, so they can still be large. But if you just go to large spatial separations, they're always small. In the ground state, again, it's in the ground state. So of course we're going to be in some excited states where we pump up. I mean, when you do Bell experiments, what you do, you start from some point, you send some stuff to two separated points, and of course then they're correlated because they're not in ground state. I mean, they're in some excited state that was designed so that there's some correlation between those 2 points, right?
Oh, it is because of the state, okay.
Yeah. I mean, if you want to formulate some Bell experiment in quantum field theory, you would do something like this. You would have some source of your particles, and you will send 1 over here and 1 over here, and then you measure this correlation, right? But that's not a ground state. It's a specially prepared state, right, where you have some correlation between these 2 points. Now I'm just talking about the vacuum fluctuation, so I'm not allowing myself to produce any particles by hand or whatever, inject any energy. I'm in the ground state, in the vacuum. And now I'm measuring, what are the because the thing is quantum, it's not 0 expectation values of anything, right? I mean, because of this, right? For ground state of harmonic oscillator. Okay, now let's proceed with the sitter. So let me. I hope it won't be confusing, right? If I start changing these formulas, no, that probably will be confusing. Let me just have a new copy of the formulas. So here we do free quantum fields. In de Sitter. Okay. So the action is now it's not hard to guess, right? We now replace the Minkowski metric eta mu with g mu, right? So we have square root of minus g, like we have in GR, and then we have d mu, let me do like this, d mu phi, d nu phi, g mu nu, right? Okay, so now let's open it up. Let's say we have our metric, which is minus dt squared plus a squared of t, and let me do like flat slicing, dx squared, okay? And this a is an exponential, but okay, we'll do it later. Let's keep general a. So we put here, so our action is, integral dt dx, and then square root of minus g is what? It's a cubed, right? So we have a cubed, and then phi dot is the same, right? Phi dot squared. But then I will have minus, I'll do this, minus a squared di phi squared, a minus 2, right? Because I have the inverse metric, so a is downstairs, so I have a minus 2. Okay? And then if I go in the momentum space, I have a cubed, and then I have phi dot squared minus k over a squared, phi k, phi minus k. Okay? Good. So now, so everything is basically the same. Okay, I now have so this thing depends on time. So what I get time-dependent harmonic oscillators, right? So first, let's go. So now let's see what is time dependence. Time dependence comes from okay. There's some overall normalization, right? And then also the frequency is also time dependent. Okay. Good. So now let's see how we can proceed. So there are two regimes. One is that k over a is much bigger than h, and then second regime is k over a much smaller than h. Okay, so of course there is a transition period, right? But importantly, there is two regions. So now, if k over a is much bigger than h, then this means it means flat space physics. And this means kind of importantly, like deeply de Sitter. I mean. So where does it come from, right? So I mean, intuitively, it should be clear that some sort of inequality should exist like this, because if I think, so now we leave kind of in space-time that I'm telling you actually de Sitter or very close to de Sitter on large distances. But of course, for when we do like experiments in our laboratories or whatever, we use flat space Fourier transforms. We don't care about this curvature, right? That's because the distances on which we operate, they are much shorter than the curvature scale of this de Sitter space-time, right? Very good. So now the slightly less trivial thing is why is it k over a? Why, for example, it's not just k that I compare to h, right? Okay, let's try to understand where it's coming from. Yes, you're right. I mean, maybe the easiest is to talk about it is from the equation of motion. But you're right. Yeah, let's maybe we can do it this way. Maybe we can do it this way again.
How do you want?
How did I? Well, let me do the equation of motion first, since you brought it up, and then I'll explain another logic. Okay. Because I want to do equations of motion anyway. I want to do them in a slightly different coordinate system, but let's do them in this coordinate system first. So when we work out equation of motion, Lagrange equation of motion, right? There will be two. So here there will be two terms, right? There will be a term which when time derivative acts on the scale factor and it acts on the second field, right? So basically we'll have equation of motion like this. Phi double dot plus 3 a dot over a phi dot plus k over a squared phi equals 0, right, in momentum space. So now you see a dot of, you agree that that's the equation of motion? So now a dot over a is just h, right? So now here's this is where the comparison is coming from. So say if I ignore this term, say I go to deeply de Sitter regime, then basically phi dot is something like h, and then I have h squared, and then basically I'm trying to see, I start from one regime and then I start to see when the other term kicks in, right? And then I see that here, if dot is h, then I have h squared, same as k over a squared. So h roughly k over a, that's where the transition between regimes happens, right? So indeed it's clear that it's only k over a that appears in this equation. So that's why it should be k over a that compares to Hubble, okay?
Could you how to get one more h from phi dot?
Well, it's basically when you ignore this term, right? So then we have this equation, one derivative we integrate, and we have like phi is like e to the ht, roughly speaking, right? But maybe it's better to start. Maybe it's better to start from this direction, right? Then phi dot, if we start with this term dominates, right? Then dot is like k over a because we have omega. Maybe I should say here, right? So our omega for our harmonic oscillators is k over a, right? So when we start from the deeply Minkowski regime, we ignore this term, okay? Then we have dot as k over a. It gives the same answer, of course, right? Because then this dot is k over a, and then h should become proper to k over a. That's when this term kicks in, right? Yeah, that's probably much more clear. Yeah, so it's better to start from Minkowski regime, where omega is k over a, so dot is k over a. But let's understand also the picture for our. Okay, so the idea is that the mode of the size, so when k over a is close to Hubble, then it corresponds to the mode. So, you know, when we Fourier transform the corresponding mode, so this mode with x delta x, which is, of course, 1 over k, right? When we Fourier transform roughly modes with moment to k, they correspond to functions that have some support on the distances that are 1 over k, right? So when we have this delta x, it is exactly of the size of the cosmological horizon. So that these 2 points, they start being sort of outside. Of course, these lines should go at 45 degrees. I mean, so that's what I meant to draw. Okay. So that is also something that's something one can easily check. So this corresponds to modes. Okay, all right. Delta x is 1 over k, and this corresponds to delta x, so size of the wavelengths comparable to the horizon, physical wavelengths comparable to the horizon scale. Which again just makes sense then geometrically, right? Because when will the curvature be important? When we consider fluctuation of the size that is comparable to the curvature of the universe, right? So curvature of the universe is Hubble, but you see the point is that the modes, the idea is that we do Fourier transform in x, but the physical distance, the geodesic distance between the points is a times x, right? So that is what, so a times x is the physical distance. A times delta x is a geodesic or physical distance. Right? So it's when physical distance is of the size of the curvature, right? That's when the mode is sensitive to the horizon. That corresponds to x being 1 over a, so it means that delta x is 1 over ah, and if delta x is 1 over ah, then k should be a times h, right? Okay, that's another way to see it. So the punchline is that we have this regime where we're in flat space, so we can use our result from flat space where we had phi is 1 over x, or more precisely, it was 1 over, or phi k, we had phi k, phi minus k was 1 over omega, right? So we can import this result over here, but with a subtlety, right? So here we also have this overall a cube sitting in front, right? So because we have it's yeah, I'm running out a little bit. Okay, let me erase this thing. So we could have a let's define a canonical field, phi k canonical, which is a to the 3/2 phi k. Okay. So then it would have and then we're in Minkowski, and this makes sense in Minkowski region. That is k much bigger than h. Okay, so now this phi k, phi minus k canonical would be 1 over omega, that is, it's going to be A over K, right? From which it follows that phi K, phi minus K will be then, and then I should get 1 over K, A, and then 1 over A cubed, right? Good.
By the way, what do we want to get?
We want to compute the expectation value. Yeah, thanks for asking. We want to compute the expectation values of, say, two of these fields, just because it's the simplest thing that is non-zero, in de Sitter spacetime. But I want to avoid a careful quantization of quantum fields in de Sitter spacetime. And actually, in any case, it will be necessary for us to use some analogy with the Minkowski space. So I'm trying to utilize our results for Minkowski space, that is this thing, to derive the answer for de Sitter space.
Okay.
So, and first by going to this region, so we're going to this region where momenta is large when we're in Minkowski space. So I'm just copying the answer from Minkowski space, but we need to do a careful rescaling, right? So this is 1 over omega, right? Because omega is K over A. But I had also this prefactor A cubed, right?
So, am I right that this rescaling of phi is important to get flat?
Yeah, because if I get, okay, I can write it down, but if I define the canonical thing, then the Lagrangian basically removes.
Yeah, it is literally will be canonical in flat space.
Yeah. And it's subtle. I mean, of course, if I just remove there are some dots, whatever. But because we're in this regime where h is small, then I do not care about it. Okay.
Yeah. Okay. It's clear.
Good. Any other questions? Good. So this is the regime that is true for this large K. So now, if we go to K, so this is true up to, and okay, let me do an approximate thing, and then I'll do a slightly more careful thing. Okay, but let me first do. Oh wow, we're running out of time. Let me wrap up. Let me just do the approximate thing. So then the idea is that when A over K approaches, when K over A approaches H, then modes go out of the horizon, so they stop communicating with each other. So the 2-point functions should stop changing. Okay? So the idea is that so it stops changing. So now, how do we compute a 2-point function at a given K, where K over A is much smaller than H, which is what we eventually care about. We care about this very long distance, so very small K. Okay, good. So this corresponds to evaluating this object at a time where K over A is equal to H, is equal to phi K, phi minus K at T such that K over A of T is equal to H. Meaning A of T equal to H to K over H. So all what's needed is to plug in a of t equal k of h into this equation. So you see the idea is that we're in flat space, okay? And then, so k is fixed. It's just time changes. So it's a bit like a diabatic approximation in quantum mechanics. So time is changing, okay? K is fixed because they do not talk, different k's, harmonic oscillators do not talk to each other. And then, it just stops changing, okay? And so then, so what is the value? The value is then we need to substitute. I can substitute k over h over here, okay? And what I get is 1 over k cube, and then here I have h squared, okay? Okay, sorry, so this is, this I only got it in this not so careful way. So to get it in a careful way, what one needs to do, one needs to solve the mode equation. And you can actually solve it analytically and basically see how the wave functions of this harmonic oscillator evolve with time. So it's like a time-dependent harmonic oscillator. You can actually solve it analytically. You can see how the wave function changes with time. And then you get, you get a precise formula that interpolates between 1 over k, between this answer at large k and this answer at small k. Okay, but okay, I mean, I don't have time to do it because I want to then wrap up and say what are the conceptual implications. So now, but this result is super important. So this is what's called scale invariant power spectrum. So it was conjectured by Zildovich by sort of just looking at the sky somehow and saying that they should be scale invariant. But then Mukhanov and Chibizov were the first to compute it in the actual inflational scenario. I mean, they did a more complicated calculation, but actually applicable to real world. But they were the first to get this from inflation.
So haven't we used that we have exponential law of
exponential law? Yeah, because this is, it was important that there is a horizon for the logic, okay? And then they actually, the fact that, that it's exactly 1 over k cube and the fact that the Hubble is constant, so I used all these things, right? So if Hubble was not constant, it would be a bit more complicated too. Logic, something conceptually like this you would get every time you get a horizon. But really this formula that is so simple was here also because Hubble was constant, which basically limits me to exponential expansion, right? Good. So now let me try to wrap up. So now this we can Fourier transform. And Fourier transform 1 over k cube, I'm in 3 dimension, gives me phi of x 1, phi of x2 going as log x1 minus x2. So you see, instead of having 1 over x squared as we had in flat space, here we have a logarithm that is even grows, but okay, logarithm is basically constant. So that is the manifestation of this statement that it stops changing once they go outside the horizon. So as distance is longer than the horizon, the spectrum is logarithmic. This is what's also called scale invariant really applies to logarithm, okay? Because yeah, sorry. Expectation value or whatever, or correct. Okay, good. So now let me try to put all of this together. This is true for free quantum fields or weakly coupled quantum fields. So now what is this? The piece that's missing is to connect to what we had before, okay? So what happens? What happens over here? And then we have our Penrose diagram, right? Okay, I copied it. So now, what happens over here in the reheating surface? RS, reheating surface, which is somewhere here. This is time goes up. This is conformal time going up. This is A, right? So basically, the simplest model for inflation is that we have some scalar field. Okay, there are many pictures, but anyway, some scalar field with, let me call it capital phi, that has some potential that is sort of like this, that is basically constant over here, and then it decays. That's the simplest model for inflation. So here, it's like we have a cosmological constant. So that produces this period of exponential inflation with a large positive cosmological constant. But field is slowly rolling, and then eventually it falls down, okay? And this cosmological constant, so this goes to 0, becomes much smaller, okay? Now, so this is the homogeneous picture. It explains transition from here to this power law, okay? Now, this field has some fluctuations. Plus little phi of xt. Now, these fluctuations, they basically can be modeled as the free scalar field. Now, this free scalar field, because it fluctuates, it will not simultaneously reach this region everywhere in the universe, okay? But instead, this point will have different time delay or time advance in different parts of the universe according to the fluctuations of the perturbation of this quantum field. That actually, the correlation, the expectation value of these perturbations is described by this formula. Okay, because basically corrections, because here is basically free field. Its perturbations behave in the same way as here. And as I said, we're insensitive to what's going on over here, because you see, I never needed to specify for you the initial conditions for this field. What I had to tell you is that once it was at early enough times where this A over K is small, I was in Minkowski vacuum. So that what justifies irrelevance of these initial conditions, that everything is happening over here. Actually, this quantum fluctuations on, say, these scales get produced somewhere over here, just as a ground state vacuum oscillation of the harmonic oscillators. And then they transition into this regime so that the spectrum freezes. So here we have just the ground state fluctuations. Then here they become these frozen fluctuations with logarithmic spectrum, and they delay the transition from inflation to power law differently in different universes. So clocks are kind of desynchronized in different universes because inflation ends at different times. So because of these, different parts of the universe expand slightly more than the others. And that is the thing that later gets multiplied by the gravitational potential and produces this structure in the universe. So that is roughly the picture. Okay, let me stop here. It's more or less what I was. Okay, I didn't get to these other topics of connection to anti-de Sitter and the sphere, but okay, that's a bit more technical and probably less important and was a bit too ambitious for 2 lectures. But okay, but I hope I gave you some flavor, you know, which things you need to know how to compute to be able to do these calculations for quantum fields in cosmological spacetimes, and maybe it is there is some hopefully there is some clarity to what is this idea of the generation of the classical fluctuations from the quantum mechanical ground state fluctuations of quantum fields. Okay, yeah, let me know if there are any questions, but otherwise that's it.
Maybe we can discuss some reference for this.
Good, yeah. So there is a good. There are many references on this. I think a good lecture from which I kind of good set of lectures is lectures by Leonardo Senatore, where he follows the similar logic. I mean, it's for fluctuations. This is an archive number. Okay, so this is Senatore. Yeah, so he does this similar derivation of the power spectrum there, and but in more details and more carefully.
And that was free theory, but when we switch on interaction, we will have problems.
We will not have problems. If fluctuations are perturbative, this will still be true, but it will have some corrections to it. And for example, we can then compute, for free theory, if you know the two-point function, you know all expectation values, right? Because they're just, say, expectation value of 4 operators, just the product of expectation value of 2 operators, right? That's what's true for free theory. So now for generic, when we have interactions, that's no longer true. So we need to describe fully the spectrum of perturbations. We need also to compute higher point correlation functions.
Because as far as I know, when we switch on interaction, we have problems with unitarity in the de Sitter space.
Well, not really. Sometimes people say something like this, but from all we know for sure, there isn't any problem. In perturbation theory, in quantum field theory on the Sitter space without gravity, there is definitely no problem. You can define it non-perturbatively. When we have perturbative gravity, as we have in inflation, the first problem that comes to us is how to define observables carefully. And that's what I discussed, and we acknowledge that that's complicated, but in inflation, because, as I said, we have this meta-observer, whatever, and gravity is weak, especially over here, we can kind of perturbatively proceed and everything's fine, and there is no problem with unitarity. So sometimes when so this idea that I told you, that it's short distances, we actually equivalent of flat space. So this is something that some people have actually problems believing, because you can, well, I don't know, it's not, to me it sounds very natural, and I think we can, at least in perturbative quantum gravity and non-perturbative quantum field theory, that there are many consistency checks that this procedure works and at least self-consistent and well-defined, but it's true that it's not like an axiom, and somehow some people have opposite intuition. They say that the de Sitter space at short distances should look very different than Minkowski space. Okay, so this is where these claims are coming from. But to me, that does not sound very well justified. But it is also true that there are some ideas of maybe how to construct some alternative theories for this region of space-time, or alternative states for the same theories, because there are several things. There are a few things you need to specify. One is how your space-time, what's your theory here, but then also what is your state here. So I told you the state is irrelevant, because I said, well, no matter what state you put here, I can predict these fluctuations just by using this flat space logic. But at least my state should be not too crazy. It shouldn't be like a very highly excited state, in some sense. If it's a very highly excited state, then it may fail this logic that at short distances we're close to the ground state of Minkowski space. But okay, there are something I wanted to talk about is the Hartle-Hawking or no boundary state, which is like one version, how to put it in some more non-perturbative context that does have this property. And okay, but this Hartle-Hawking state is Hartle-Hawking.
Hartle-Hawking is one with a complex-like metric.
Yeah. But I wanted, that's when this connection to the sphere, etc., that's where it becomes important, but I didn't have time to talk about it. There is a nice recent review by Maldacena that came just out last month, I think. Juan Maldacena, who reviews the current status of this Hartle-Hawking state and others. I don't remember the archive number, but but you can find it's on Spires or whatever. It's like I think it's in March the paper came out, maybe in late February.
And what other problems with this theory, like from other side, like information paradox and
Yeah. Then there is all these things that we did not touch upon, but I sort of mentioned that the definition of all of these things once we want to talk about gravity non-perturbatively, they become complicated, and then we can expect that there are some interesting effects in de Sitter space or some inflationary spacetimes when inflation lasts long enough, because you see the longer inflation lasts, kind of conceptually the closer we are to de Sitter. Well, okay, it depends how you look, but in some sense it's true that once inflation is long, you kind of have regions that look close to bigger chunks of de Sitter space, and then some non-perturbative effects may be related to some form of kind of discretization of space-time in quantum gravity, to the extent that, well, discretization in a sense that we expect some number. So in quantum field theory, we have infinitely many of harmonic oscillators in arbitrary small region of space-time, right? So in quantum gravity, we somehow don't expect that. In quantum gravity, we expect that in any finite region of space-time, space, let's say in any finite region of space, we should have finitely many degrees of freedom that do not exceed the entropy of a black hole of the similar size. So that follows from some consistency checks in gravity, from some examples where we understand gravity non-perturbatively. And from that, we can expect that also in de Sitter space, the number of degrees of freedom is finite. So something should happen with this infinitely many degrees of freedom that we can naively put on top of it, just putting some quantum field on a quantizing metric in de Sitter space. But no one really knows how to make that thing precise. So that the idea is that maybe indeed that there is something should cut off this, some quantum gravity effect should reduce the effective number of degrees of freedom, and that could also potentially limit the maximum length for which the spacetime could be expanding, because you see the conflict with unitarity that naively appears is that if spacetime is expanding forever, where the new degrees of freedom are coming from. But in the quantum field theory on de Sitter space, there is no problem, because originally you have infinitely many degrees of freedom in any finite region of space-time. So kind of it's infinity that grows, but it stays in, all infinities are sort of equal to each other, All infinite dimensional Hilbert spaces can be mapped into each other, right? So you cannot really formulate a paradox. But if on top of it you somehow say, but well, no, gravity should limit for me the number of degrees of freedom, then you start having something a little bit similar to this information puzzle for black hole. But again, no one has formulated precisely such a paradox so far. So there is some feeling that something interesting should happen if we insert this, if we properly understand this quantum gravity effects, these non-perturbative quantum gravity effects that limit the number of degrees of freedom. Related to some Bekenstein-Hawking bound or whatever version of it, but we do not know how to make it concrete so far.
In this formalism, we never discussed a back reaction of the
No.
matrix.
This can be done. I maybe even mentioned it last time, but of course I did something. I wasn't able to show the actual calculation. Basically, I told you that there's a fluctuation of this clock field, but I sort of told you, right, that it changes by how much the universe expanded, right, and that is the gravitational degree of freedom. So actually back reaction is included in this calculation when done carefully. So you can think of it. It's actually you can think of it as by using diffeomorphisms. You can again reshuffle these fluctuations of this field into fluctuations of the metric. That's the same thing. And physically, they're more like the metric fluctuations, because I told that's how much the universe expanded. So that back reaction is included in this calculation when it's done with all the details.
Could you explain one thing? You said that it is impossible to measure in de Sitter correlation function, but as I understood, it is literally the correlation function.
Yeah, but I told you, right, that we are not, like, if we were in a pure de Sitter, like with the dashed line, we would have problems measuring this. Say this correlation function produces some correlation between, say, these 2 points, right? So this is my phi here and phi here, phi of x1, phi of x2, right? But the reason I was able to measure it because there is some, signal that's sent from here to us and from here to us, and then we measure it, okay? So that was important, that we're not in the pure, if we had this dashed line, they would not be able to communicate these points anymore, whatever, if you draw them a little bit further apart. They're not able to communicate anymore, and then you do not know how to measure it.
Why they would not talk?
Well, because of that's what I was explaining, right? Because of the horizon. So let's say we have this dashed line that cuts off the space-time. Say this is point 1, this is point 2, right? You try to have like a single device that can receive signal from both of these points. And you cannot, right? Because this point has a future light cone, which is this. This point has a future light cone, which is this. And they do not overlap, right? The reason that the future light cones overlap is because we extended our space-time.
Okay, but is it possible to compute S matrix in the signal?
Well, as we compute, you can compute many things, and people define, what is an S matrix and de Sitter. But in pure de Sitter, it's not clear if it's some observable or not.
So, am I right that it is in principle impossible to compute any observable things in the Sitter space?
Well, okay, I know you can draw. I said I was a bit more careful. I said we do not know yet how to define any single observable in the Sitter space that is well defined with fluctuating metric and especially when we want to treat quantum gravity effects non-perturbatively. So that is true. If it does not exist at all, or if we didn't figure out how to define it, I mean that we'll see.
Okay, I heard that some people used to calculate this S matrix in inflation, and they wanted to understand does optics theorem is works or not.
Yeah.
And, so how if it is impossible to?
No, well, there are some questions whether, first of all, many calculations are done, perturbatively, and second, many of them are done in a sense, at least in mind, people have something like inflation or pure de Sitter, where you have this extra handles, you have some preferred time foliation due to the constant lines of constant inflaton field and all of this. So there are many details that are important in these calculations. But also, so this, I don't think that this S matrix that people propose there, and also the version of unitarity that they check, so far is only perturbative unitarity. It's not like a full non-perturbative unitarity like for S matrix. Like S matrix is exactly like SS dagger is exactly 1 as an operator, right? And for this de Sitter S matrix, it's not like this so far. It's some perturbative statement.
Okay. And am I right that if we set Hubble to constant, we will get flat spectrum always? So it is only one condition for getting flat spectrum.
You mean? Yeah. In pure de Sitter, for massless field, the spectrum is whatever scale invariant or flat. Yeah. Flat is not the same as flat space, right? Flat means scale invariant.
Yes.
1 over k cube. Yes, or logarithm x. Yeah, this is a property of the de Sitter space, which is the only space for which Hubble is exactly constant, right?
So, and does it matter what initial condition you have?
Well, I was trying to tell you that it does not matter to a certain extent, right? Unless your initial conditions are some very highly excited state, then this is going to be true. Of course, you see, if you have some initial conditions, it's true for modes. What I used here is that I evolve my mode say we fix some k, fix the size of the mode. We evolve it back into the past, by just changing time, and its physical momentum evolves as k over a, and a decays exponentially, right? So k over a grows exponentially. And then if this mode becomes inside horizon mode before it hits, I don't know, some singularity, okay, then I can use my logic. Now, if the mode is of the size of the entire de Sitter space, no matter how fast I evolve it, it simply never goes inside the horizon, right? It stays of the, and then of course I'm sensitive to singularity. But if my mode is small enough, then if I evolve it, it eventually goes inside the horizon and then becomes a flat space mode.
Okay, but why do people usually set flat initial conditions, flat wave initial conditions for phi?
Well, that's because
It doesn't matter.
No. It matters that we said flat. I'm just trying to. It doesn't matter what the universe does very far in the past, as long as we, on some of the modes that we care about, we can set Minkowski initial conditions for them. Well, okay. The point is the following, that, let me draw a bigger picture.
So my question is, does it matter to set flat wave initial conditions for phi or not?
These are not really kind of absolute initial conditions. Say we have something complicated here, okay? Then I have my mode. Say this is the mode that I care about, okay? This is the mode. I evolve it back. Now let me draw the horizon scale for you, okay? Horizon scale does something like this. Horizon scale is this, right? So here, this mode is much bigger than the horizon. Here it's equal to the horizon. Here it's very deep inside the horizon. I'm saying here, I use flat space physics no matter what happened here. So here I have some wild fluctuations, but here I say I have something close to de Sitter, meaning that here I have Minkowski. And that's all what matters for this mode.
Okay, it is clear. And what does it mean that it is not important what initial condition we have for phi? When you said it, what?
Yeah, that I said that this, it's not important. So here, phi, maybe it had something complicated over here. I said it's not important because this mode was so tiny in here that basically it has no, it's completely lost over here. It's enough to fix this mode at some intermediate times. So initial conditions I put really not asymptotic, they're at some intermediate times because already here, this mode is very, very short.
We should put flat wave initial condition.
Yeah, because this is just saying that here I have something like Minkowski.
Okay. Okay, it's clear.
That's because this part of space-time basically came out of nothing. So, and then I don't need, you see?
Yeah, it is clear.
This region of space-time, it was smaller and smaller back in the past to the point that it's kind of above the cutoff that we do not care. And then when it becomes of some string scale or whatever it is, that's where I use flat space physics to impose. But back in the past, that region of space-time basically didn't exist, so I didn't need any initial conditions for it. That's the logic. Да?
Как я читала, у нас возникают проблемы еще на этапе квантования полей на искривленном пространстве, начиная от того, что мы не знаем, как... у нас нет однозначно определенного вакуума, и заканчивая тем, что не очень понятно, что такое упорядочивание по времени. А вы так просто написали корреляторы, и все так хорошо.
Сейчас, извиняюсь. Мне пришло просто сообщение, я прослушал немного.
Я понимаю. Я говорю, что, насколько я знаю, у нас с квантовой теорией поля возникают проблемы еще на этапе квантования, собственно.
Мгм.
Что у нас неопределенный вакуум, что мы не знаем, что такое упорядочивание по времени. А вы так просто написали коррелятор, если так хорошо.
Ну, не, ну это все, да, как бы такие технические вопросы, но они более-менее решаемые. В терминах квантовой теории поля на деситере это как бы все решаемое. Ну, я говорю, в терминах гравитация, пертурбативная тоже это все решаемо, да. Тут нет, ну это есть там информализм, там, ну вот я думал про это немного больше рассказать, про там поворот деситер на сферу, ну как бы такие технические вопросы, они более-менее все решены в рамках теории возмущений, по крайней мере.
А как решение вопроса с неопределенностью вакуума, или фиксируется Банч-Дэвис?
Ну не, ну вот то, что я сейчас рассказывал, это и было в принципе про фиксацию вакуума, да. Это то, что называется Банч-Дэвис, он же Хартл-Хокинг, там, ну как бы в рамках теории возмущений это все эквивалентно. И сводится к тому, к предположению, что на коротких расстояниях это Минковский.
Слушайте, а вот еще ищут не гауссовость у этих пертурбаций, а в какой момент вообще в уравнениях видно, что там гауссиан это или нет?
Ну, это вот полностью Гауссу, потому что теория свободная.
А как? Ну как увидеть, что мы используем, что это гауссовидная формула этой волны?
Ну, Гауссова это то же самое, что свободная теория поля. Это синонимы. Я сделал свободную, поэтому это будет. Гаусс это, что я сказал, то, что многоточечные функции это произведение двухточных функций.
Понятно.
Взаимодействие Гауссова это синоним свободный.
Ага, понятно.
Не, ну с упорядочиванием по времени это тут нет никаких проблем. Нет, выделенного, ну в инфляции совсем нет проблем, потому что у нас есть инфлатон, который задает preferred time slicing. Это не как вектор Киллинга, но есть выделенная фоляция, выделенная слайсинг, как это, в общем, понятно. Дальше, в чистом деситере, в деситере, где нету гравитации, ну там просто выбираешь любое время и по отношению к нему квантуешь, и поскольку изометрии там гарантирует, что все будет одинаково, какое время не выбери. А дальше, ну если есть как бы гравитация в чистом деситере, ну вот я говорю опять же, пертурбативно, ну там как бы понятно, что делать. Там не пертурбативно, ну да, вот это вот проблемы, о которых я говорил, ну нужно рисовать какие-то геодезические какие-то там и так далее. Через что? Ну, функциональный интеграл, это же тоже. Ну, функциональный интеграл, вот он полезен в основном для всяких как бы семиклассических непертурбативных эффектов. Если мы делаем теорию возмущений, то функциональный интеграл как бы это же просто переписывание гамильтонного квантования. Не, но это геодезическая, это как бы физическая вещь. Ну, не, ну есть такие как бы идеи, так немножко это обобщает то, что вы говорите, какое-нибудь там БРСТ-квантование делать. Когда у БРСТ-квантовании, да, калибровочная инвариантность, она как бы очевидна, ну, но унитарность не очевидна, да, становится. Ну, насколько я знаю, никто это особо не изучал. Ну, это вот такое как бы, но это, в принципе, интересно, можно было бы поизучать. Но, по-моему, аккуратно это никто не делал. Вот. Но, ну, наверное, то есть будет какой-то закон сохранения сложности, то есть будет как бы сложно понять, как унитарность сохранить, но было бы забавно, да, посмотреть на каком примере, что там с наблюдаем получается.